Hello everybody, welcome to EET 1104, 1134. I must apologize, this video is getting out a little late for yesterday Monday's lecture. I had a little plumbing incident at home which caused some flooding, so my day yesterday was taken up by matters not related to school so much. But let's go ahead and get started on chapter 10 and talk about these things called capacitors. Yay, we're finally getting away from resistors. Well, let's first of all, let's talk about what a capacitor is. We can think of a capacitor in its simplest form as two plates of some kind of conductive material. They could be copper, aluminum, steel, iron, gold, silver, some kind of conductive material. And if those two plates are in parallel to each other, and we connect across those plates some kind of voltage source, what would happen? Well, according to the Benjamin Franklin way of looking things, we would start, since this is positive on this side of the battery and negative on this side of the battery, we are applying energy to these plates, and the result will be is that positive charge will start to build on this plate and negative charge will build on that plate. And so positive here, positive there, negative there. What we get in between those two plates is a voltage that builds up. Now, how long does it take for voltage to build up across the plates of a capacitor? Well, we're going to talk about that. The time for, if I could spell this morning, for voltage buildup is given in seconds. How many seconds does it take for the voltage to build up across the plates, between the plates of a capacitor? Well, it depends on a variety of things. What kind of material is in between those two plates? We'll probably just, for the most often, just call it air, because air is easy to work with, but we could have some kind of insulating material other than air, maybe some kind of plastic material such as polyethylene or paper, or maybe an oil. But between the two plates we have some kind of material that is an insulator, and that material is called a dielectric. So that material in there is called a dielectric, or an insulator. So we have this capacitor, we apply a DC voltage to it, and we get charge that builds up across the plates. And that charge will build up until it reaches its maximum voltage potential. So what is the maximum voltage potential of a capacitor? Well, the voltage max for a capacitor is equal to this. It's equal to its Thevenin voltage times 1 minus e to the minus tau. This should be more of a squiggle here for the Greek letter tau. This is supposed to be a tau right here. That tau goes right there. So this is what we call an exponential equation. And what does an exponential equation do? Well, in this form it describes a curve. So if we have a capacitor and given some kind of time and some kind of voltage, the voltage for the capacitor, assuming there was no voltage applied to the capacitor to begin with, it starts at 0. So we start at 0 volts and we start climbing. And the curve is an exponential curve. In this case, it's a rising or increasing exponential curve, and it curves until it starts approaching some value, and that value is called its V Thevenin voltage. Now, how long does it take to get to that value? Well, time is in seconds. We've got this thing called tau. Now, the time from here to here isn't tau, but it's actually 5 tau, where tau is called the time constant. So let me get things sorted out here. So tau is called the time constant. And it takes about 5 tau to achieve max voltage. And what is the max voltage? Well, it is given by V Thevenin. Okay. So tau, where does that come from? Well, tau is given by the Thevenin resistance of the circuit times something called capacitance. Well, what is capacitance? Well, capacitance is a measurement of the capacitor's ability to withhold a voltage field given some certain parameters. I'll let you read the textbook to figure out more about capacitance and what that actually is. But we can talk about the units for capacitance. Hold me, I got to put you on pause here. Yes, Jacob? Okay. Okay. Okay, thank you, sir. Okay, bye. Okay, are we back here again? I hope so. There we go. Pause, okay. Okay, looks like we're still good to go. Okay, so, excuse me, I had a little interruption here, so there may be a little jiggle in the video as I do some editing. So, tau is given to us by the Thevenin resistance of the circuit, seen by the capacitor, times its capacitance, where the units for capacitance are given in something called farads. Now, the farad itself is actually a pretty large unit. So when we look at capacitors, typical values for capacitors in what we call microfarads or picofarads. And microfarads would be given by the symbol mu f, and pico is little p f. So microfarads are e to the minus 6 units, or pico and e to the minus 12. Well, what happened to nano? Well, for whatever reason, typically you do not buy capacitors in nanofarads. They're either in microfarads or picofarads. So if they're a nanofarad size capacitor, then we talk about in terms of thousands of microfarads. That is the convention that we have. I don't know where that convention says we need to eliminate nanofarads, but that's the way it is. So the units for capacitors are in farads, usually either in micro or pico. Anything that gets to be, I said thousands of farads. For nano, it'd be 1,000ths of farads. So, 0.01 microfarad would, in other words, be like 10 nanofarads. But if we just say microfarads for whatever reason, it's not thousands but thousandths. Okay, so let's talk about the voltage of a capacitor and how we'd find that. So we need to find the Thevenin value for the capacitive circuit. And so how do we do that? Well, we do it just like we did in chapter 9. Just a little note here. I noticed there were a handful of students on this last exam who just seemed to be resistant to doing nodal and mesh analysis. They used chapter 5, 6, and 7 techniques to solve for the circuits on this exam. I would really encourage you to get away from that and start using mesh and nodal techniques from now on. That's going to serve you better, especially for the final exam. The circuits are going to be a little more complex now, so let's make sure we're doing things by the nodal and mesh method. So let's go ahead and let's just create our little capacitive circuit. And we're going to keep it simple for now since it's just introductory. So we've got a voltage supply, and we have some resistance in the circuit, and I'll go ahead and throw in another resistor or two just to keep us a little bit honest. Let's do something like this, and then out here on the end of the circuit I'm going to throw in a capacitor, and the symbol for a capacitor is just something that looks like that. These two lines are the same length, and we have some kind of parallel plate capacitor here. And let's just give a nice voltage source of 10 volts, and let's say this is 5 ohms, and this is 8 ohms, and this is 3 ohms. And we've got a capacitor here, and it needs to be of some size. Let's just go ahead and say it's 100 microfarads. And first of all, what's the first step if we want to start analyzing this capacitor and what it's going to be doing in the circuit? Well, step number 1 is find the Thevenin voltage. And how do we typically find the Thevenin voltage? We do nodal analysis, or we should be getting in the habit of doing nodal analysis, hopefully. Okay, so where are our nodes? Well, we've got one here, and we've got one down here. Since this is a lower voltage side, we'll go ahead and call that 0 volts here. So then we have one node voltage up there that we do not know. And so what are we going to do with the capacitor? Well, since we're finding its Thevenin voltage, we'll take the capacitor out and leave it open. So let's remove the capacitor and leave an open gap here and find that Thevenin voltage. Okay, so do we need a node here? Well, this already here is now included in that node. Do we need a node there? Well, the question I'm going to ask is there a current through here? Is there an I? Does it exist? And since we have an open gap here, no, the current does not exist. If there's no current to this branch, is there any voltage across that resistor? And the answer to that question is no. There's no voltage to that resistor. So we can just essentially ignore that resistor. And this node comes out and grabs that also now. Since that resistor effectively goes away, this just becomes a wire going out to nowhere. And so whatever the nodal voltage is here, it extends out through here. So indeed, we only have one nodal voltage that we need to find for this circuit. And to find nodal voltage, we sum currents for that node to find the voltage. Sum currents to find the voltage. We've got a node here, a wire to the left. Start at this node, work down to the next node. V1 is the voltage there. Subtract any voltage we see. We have 10 volts, so we subtract it. Subtract the voltage of the next node, which is 0. Divide that by all the resistance we see on the wire. In this case, it's 5. Okay, so that takes care of the current on that wire. This is the current on that wire. We'll go to the next wire, and there's a current on that wire. This node to the next node, so that's V1 minus 0 over any resistance we see in that wire. We look to the wire to the right, and we've already determined that there is no current there, so there's no term to write for that wire. We have this current and this current, and the sums of those two currents in the Thevenin circuit is simply 0. Why are we finding the Thevenin voltage here where the capacitor should be? Because we want to know the maximum available voltage for that capacitor. And V Thevenin is how we find the maximum available voltage. So let's resolve this circuit. We've got a V1 over a 5 and a V1 over an 8. That takes care of that term and that term. We're left with a minus 10 over 5. Now we'll go ahead and just pull it to the other side, so that becomes 10 over 5 or 2. So we have a V1. Now I can just simply take this term to the other side and divide it out. It would be 10 over 5 divided by the quantity 1 over 5 plus 1 over 8. And let me fire up my calculator real quickly. We have a 10 over 5, which is a 2. And then we have a fifth. And then we have an eighth. Add those together and divide. And the Thevenin voltage is about 6.15 volts. Okay, so we got the Thevenin voltage. Now we need to find the tau, which is R Thevenin times C. Well, this is a pretty easy circuit to look at. We put all the resistors back in, and then we pretend that this voltage source, we remove it, so we short it when we remove the voltage source. Remember, whenever we remove a voltage source when we're analyzing a circuit, we always replace it with a wire. So I'm going to replace this voltage source with a wire and just look at the resistors of the circuit, and I'm going to go ahead and put this resistor back in. So I look from the point of the capacitor, looking back into the circuit, I see 3 ohms, so we're trying to find R Thevenin. So we see a 3 ohm capacitor. We get to this junction, things split off, so 5 is parallel to the 8. So we have 5 ohms parallel 8 ohms. So the Thevenin resistance of that circuit is 3 plus 5 parallel 8. Whoops. I pushed too many buttons on my calculator. So we have 3, and then we have 5, and then we have an 8. Get those in parallel combination, add that, and we get like about 6.1 ohms. So now we can graph or plot or sketch the voltage response curve for this capacitor. Because we know, well, we're assuming that there was no voltage applied to the circuit to begin with, so that the capacitor has no voltage across it at time 0. So we're going to start at 0 volts, and we're going to climb up to 6.15 volts, and it's going to take 5 tau, where tau is the Thevenin resistance times the capacitance. So let's go ahead and calculate tau. Tau will be the Thevenin resistance of 6.1 ohms times 100 microfarads. So 1 tau, 6.1 times 100 microfarads gives us about 0.61 milliseconds. Multiply that by 5, and so 5 tau comes out to about 3 milliseconds. So once we connect that capacitive circuit there to voltage, it's going to take about 3 milliseconds for that capacitor to charge up. So we're just going to sketch it where we have time in seconds. So let's say this is 1 millisecond, 2 milliseconds, 3 milliseconds. And this is our voltage. Start out at 0 volts, start out at 0 seconds. And so after, a brief amount of time, in this particular case, we're going to charge up to about 6.15 volts. And try my best to draw an exponential curve here. And here we've sketched the voltage response for that capacitor. Actually, it's a little bit steeper in real life. Probably should have done something more like this. Oops, level up there. It has pretty steep response at first, and then quickly starts to level out. But this first millisecond here, we actually probably reach about 90% of its maximum value. So this should be bumped up a little bit, but we're just sketching, so we'll live with that for now. As we get into a couple of lectures later on, we'll actually start doing plots, plotting the points. But right now, I just want you to give you an idea of what this is going to look like. Okay, so we talked briefly about the voltage response of a capacitor. Let's talk about the current response. For a capacitor. Well, we've got our capacitor here again, and we attach some kind of voltage source here. So here's our C, and here's our voltage. So what happens the moment we attach voltage to a capacitor? You might think of the capacitor as a storage tank. It's a very common illustration used for capacitors. Storage tank, we're going to store electrons. The tank is empty. The moment we apply voltage to it, those electrons start rushing through that wire, and immediately we get this jolt of current, if you want to think of it such. And as the current hits those capacitor plates, what begins to happen? Well, we have a voltage field that builds up between the plates. As the voltage field builds up, it gets harder and harder for the power source to push electrons on that capacitive plate, so we'll get something that looks like this for current over time. It'll start at some maximum value and quickly drop off towards some value approaching 0. And this maximum value up here will be I Norton. And this time right here will be 5 tau. Whatever the tau is, the Thevenin resistance of the circuit times C. Well, let's just go ahead. Oh, and we've got an equation for this curve. This is a decreasing exponential curve. So the current of the capacitor will be I Norton times e to the minus tau. A rising exponential curve is 1 minus e to the minus power. A decreasing exponential curve is e to the minus exponential power. So this is a decreasing curve. The other equation we had before is an increasing curve. Those are the kinds of things you want to make sure you get in your notes. So let's go back to our previous circuit that we just worked. We had a 10-volt source. We had a resistor there. We had a resistor down here. We had a resistor there. And then we have a place in here where we're going to stick our capacitor. This was 5 ohms, this was 8 ohms, and this was 3 ohms. So we want the current response. Well, first off, we need to find I Norton. Find I Norton. How do we find I Norton? Well, usually that involves mesh analysis. And since we're looking for Norton, we take this capacitor out and we replace it with a wire and ask the question, what is that short circuit current? So we do mesh analysis. And so we sum voltages to find those currents. We've got I1 times 5 and 8, which is 13, minus I2 times 8. Then we have a voltage here of minus 10. Take it to the other side, it becomes a positive 10. We have our second mesh loop. Minus I1 times 8 plus I2 times 8 and 3 make 11. No voltage source, so that just sums up to 0. And then we build our matrix. And let me make a little note here about matrices. Matrices are pretty easy to use using the Word equation writer program. And so I expect on the final exam, if you have a matrix or matrice to fill on an exam, you should use equation writer. And where in the world is equation writer in Word? If you go up to the toolbar across the top on the far right end, there's usually a little icon that says EQ or equation or add equation or something like that. That is your equation writer. Maybe here in a couple lectures I'll take a little time quickly to show you how to do that. Okay. Because on the last exam I was really trying to chase people's work. People were adding pages to the end of the exam to show work, and some people were showing their work on the exam, which is much easier for me to do. And so when it comes to the final exam time, I definitely want a certain format we're going to follow. And if you learn to use equation writer, that will be of your benefit. Okay, so we got this matrix. Our first term here is 13, then we have a minus 8. And there's 10 volts there. We have another minus 8, and 11, and a 0. So we get our values quickly here. So let me fire up my calculator. Go in the matrix mode, and this is a 2 by 2. Oops. And first term is 13, then a minus 8, and then another minus 8, then an 11, and then we go here to my 2 by 1, we get a 10, and a 0, and call up my first matrix, get its inverse, call up the second matrix, multiply the 2, and we get 1.392 amps and 1.013 amps. Okay, so I Norton, the current through here will simply be I2. So I Norton is equal to I2, which is 1.013 amps. So this is our I Norton value. Since it's the same circuit, tau is the same as it was before. So tau, 5 tau, came out to about 3 milliseconds. So if we sketch the curve here for current over time in seconds, current in amps, I Norton came out to be about 1.013 amps, and so the curve will approach that, and after about 3 milliseconds it's going to be approaching its maximum value of about 1.013 amps. And if we actually wanted to plot that curve, then we'd use the equation, I for the capacitor equals 1.013 amps times E to the minus tau, and tau was like 0.061 seconds or something like that. And so we've got the initial ability here to be able to sketch the voltage and current response curves for a capacitor using the I Norton and V Thevenin values for that circuit. Hopefully that'll help you get started a little bit, and then I hope I will be back on schedule for tomorrow's lecture. But otherwise, everybody be healthy.